Alrighty guys, so as you can see here from your warm-up, we are headed into lesson 11.1. Wait a minute, last we talked we were on lesson 9.3, right? So the rest of chapter 9, not gonna do it. Chapter 10, not gonna do it. We're going real bare bones here, trying to cut down on stuff because of our distance learning situation. But the first half of chapter 11, excuse me, is very important. It's on an idea called limits. Actually, we've done a little bit of exploring about this idea already. Way back in chapter 2, we started a kind of an introduction on this. So limits are hugely important for calculus, and some of us are headed into that course next year, or maybe we'll take a calculus course at some point in college. Limits are the idea that all of calculus is based on. So it's very important for us to understand what they mean. Without limits, a lot of the rules that we have in calculus wouldn't work. Okay, so what we have here is a warm-up, though, is just some plain old algebra. So take a minute, if you haven't already, to do this warm-up. Tell me where that function is undefined. So you decided it was undefined at x equals 2, right? Why at x equals 2? Well, because if x equals 2, the denominator 2 minus 2 is 0. And I know that the function's not defined if I divide by 0. Okay, so it's undefined at x equals 2 because that makes my denominator equal 0. But what's happening on the graph at x equals 2? So we know that that's some kind of a point of discontinuity. In Algebra 2 and earlier in our course, we talked about two main different kinds of discontinuity: holes and vertical asymptotes. Do you remember how we decided which one was which? Yeah, so I'm going to factor both the numerator and denominator. The denominator's already factored. I'm going to look to see if this factor x minus 2 cancels a factor in the numerator. If it cancels a factor in the numerator, then it's removable discontinuity, which looked like a hole. Good. And if it is only on the bottom, not on the top, then it is non-removable discontinuity, which means it's a vertical asymptote. So let's see what happens to the graph at x equals 2. So here we have factored it. Oh, and we see that that x minus 2 cancels on the top and the bottom, so we had a hole at x equals 2. So what does our graph look like then? Well, if this x minus 2 cancels out at the top and the bottom, we're just left with f of x, or y equals x plus 2. That's a line, right? So it's going to look like the line y equals x plus 2, only it's going to have a hole at x equals 2. So it looks like this. So that's old news for us. But what we're exploring today is the idea of a limit, which is not what happens at a particular point, but what happens around a point. So we know that f of x is undefined at x equals 2. There's a hole there. It's not, the function's not defined there. It doesn't have a value at all. But what happens around there? The y value that we get close to as we approach from the left-hand side, so we're approaching this x value 2 from the left, so we're approaching this x value from the left. That means we're on this part of the line. We're getting closer and closer to a y value of 4. And as we approach this x value from the right, we're on this part of the function, right? As we get closer and closer to x equals 2, we're getting very close to a y value, or a function value of 4. That's what a limit is. It's what I'm getting very, very close to, the y or function value I'm getting very, very close to as I approach a particular x value. So as we get very close to an x value of 2, our y value gets very close to 4. So we say that the limit of this function called f of x, as x approaches 2, is 4. So as x gets close to 2, y gets close to 4. We write it like this: the limit as x approaches 2 of f of x is equal to 4. And I said a couple minutes ago, we actually started to investigate this in lesson 2.6. In 2.6, we were talking about arrow notation, but we saw how, we also talked a little bit about how that arrow notation corresponded to this limit notation, and we said we'd get back to that at the end of our course. So you might take a peek back at your notes from way earlier in our year and see that we've already talked about this stuff briefly. Okay. So we said already, sorry guys, I'm shuffling. All right, so calculus is the study of limits and their applications. Limits are the foundation of all the applications that we learn in calculus. So if you're headed into a calculus class next year, whether it's my calculus class or a calculus class somewhere else in college maybe, you'll see that the very first unit you do is on limits because it's the basis for everything else we do in calculus. So let's talk a little bit more about limits considering graphs. You'll see that 11.1 talks about finding limits using tables and graphs. So using a table of values is kind of interesting. It shows us that we can actually calculate as we get very, very close to an x value, we can calculate what the y value is getting close to, but also it's a method that we never really use in calculus. It's very tedious, so you might want to take a look at it. It's not something that I'm going to have us actually do this year. Okay, so we're just going to work, so it was on 11.1, finding limits using tables and graphs. We're really just going to focus on the graphs. Okay, so let's consider these three graphs. So they look kind of similar, and in each case, we're asked to find the limit as x approaches 4 of this function, which is called f of x. So sometimes we see the name of the function right here. So this one's called f of x, that's its name, right? And sometimes in that spot, we'll actually see an equation. We'll see them both ways. All right, so I'm looking to see, as I get very close to an x value of 4 right here from both the left and the right, what y value am I getting close to? So if I approach from the left, as I get closer to an x value of 4, my y value gets very close to 3. As I approach from the right, my y value gets very close to 3. So the limit of my function as x approaches 4 is 3. So, and we can see that's the actual value of the function there too, right? F of, let me write this down here, f of 4, the actual value of the function at 4 is 3. I can see because I have a point there, right? All right, now let's look at the middle one. The limit as x approaches 4, same idea. So I'm looking, as I approach x equals 4 right here, from its left-hand side, I'm getting closer and closer. I'm on this part of the function. Here's where x equals 4. I'm getting very close to a y value at 3. As I approach from the right-hand side, so I'm getting closer to an x value of 4. I'm moving left along my graph. As I get close to x equals 4, I'm getting close to a y value of 3. So my limit as x equals 4 equals my limit as x approaches 4 is 3. You see how this graph differs from this one? Look, I've got a hole there, just like in our warm-up problem. So if I were asked, what is the value of our function at 4, I would say it's undefined. My graph doesn't actually have a value there, but that doesn't stop it from having a limit. When we say the limit as x approaches 4, we're not saying what does the graph equal at 4. We're saying what does the graph get close to as a y value as x gets close to 4. What are we approaching? And then our last one, let's see, as here's x equals 4. As I get close to x equals 4 from the left, that means I'm traveling on this part of the graph. I'm getting close to y equals 3. As I approach from the right, I get close to an x value 4. I'm getting very close to a y value of 3. So here again, my limit as x approaches 4 is also equal to 3. How about my function value here? F of 4 is equal to, oh, my function actually, it doesn't have a point right here, but it's not undefined at x equals 4. I see it has a value right down here at y equals 1. So my function value at 4 is 1. So we can see in all three of these cases, the actual value of my function at x equals 4 doesn't change the limit. I'm just looking to see what we get close to from either direction as we approach 4. Now these graphs, their difference is important as we start to discuss an idea, I think it's 11.3 that we'll get there, an idea called continuity. The idea is if a graph is continuous at a particular point, I can draw all the way through it without picking up my pencil. And I can here, this graph is continuous. This graph is not continuous. I approach x equals 4, but then I skip over this point to continue. And here, my graph is not continuous at x equals 4. I approach this point, and then I'm down here, and then I continue up. So while all three of these graphs have the same limit, they're not all three continuous. Like I said, that's a preview of what we'll talk about in 11.3. It's not really our focus today. Okay, let's try this problem like we would on a whiteboard. So I'd like you to pause here and take a minute to find the limit as x approaches 4 of our function f of x, and then find f of 4. Okay, so my limit is x approaches 4. That means as I get close to an x value of 4 from both the left and the right, what y value am I getting close to? So as I approach from the left and as I approach from the right, it looks like my y value is getting very close to 7. How about f of 4? The actual value of my function at x equals 4, where I actually have a point, is down here at 2. So it has a limit at x equals, or as x approaches 4, limit is 7, but the function value is not the same thing as what my limit approaches. Again, that means it's not going to be continuous when we talk about that later, again, I think it's 11.3. Okay, so now let's suppose in a different example, now instead of being given a graph, we're asked to do the graphing. So we'll graph that piecewise function, and then we'll use that graph to find the limit as x approaches 3. Okay, so let's see here. So I have 2 pieces to graph. So this top piece is, well, that's just a line, right? Y equals mx plus b. So I'm going to start down here at -4. I'm drawing it with a pencil right now because I'm going to sketch in the whole graph, and then I'm only going to keep the part that applies to this domain. So a y value of -4, and then I have a slope of 2, so I'm going to go up 2, right 1, up 2, right 1, up 2, right 1. Hold on, to stand over it here. Up 2, right 1, up 2, right 1. Did I do it right? 1, 2, 3. That looks good. Okay. So here's that whole line. Whoa, pretend it looks straight. Okay, there's the whole line. That applies for all x values except x equals 3. Kenai, what's the matter? Where x equals 3, my function has a y value of -5. So right here at x equals 3, I shouldn't have a point right there. So I'm going to leave it open, and I'm going to show that at that x value, my graph actually has a y value of -5 down here. So my graph looks like this. Guys, do you think she's jealous that you're getting all my attention because really she would like to be talking about limits with me? Hold on. Let's see if we can calm her down. Okay, so we're asked to use this graph to find the limit as x approaches 3. So as I get very close to this x value of 3 right here, as I approach it from the left, that means I'm coming up this way. I'm getting very close to a y value of 2. And as I approach it from the right, as I approach it from the right and coming down on this part of the function, I'm getting very close to a y value of also 2. So the limit as x approaches 3 is 2. Good? Kenai's happy about it. All right, next up. So let's talk now about one-sided limits. So one-sided limits aren't actually what we mean when we say the limit. But they're a tool that we use in investigating what the limit is. So one-sided limits. So suppose that we're asked to find the limit of this function as x approaches 2. So here's where x equals 2. If I'm approaching x equals 2 from its left-hand side, so I'm on this piece of the function, right? I'm getting very close to a y value of 4. But if I approach 2 from the right-hand side, I'm on this piece of the function, I'm getting very close to a y value of 2. That looks different than the graphs we just talked about, right? When I look from the left and when I look from the right, I'm approaching 2 different y values. So as I look to closer to x equals 2 from the left, that's a one-sided limit, or called a left-hand limit. And as I get close to x equals 2 from its right-hand side, that's a one-sided limit called a right-hand limit. So a left-hand limit is the y value of the function approaches as we approach the x value from its left-hand side. Left-hand limit is what we get close to when we approach from the left. The right-hand limit is the y value of the function as we approach the x value from its right-hand side. Right-hand limit means as we approach from the right-hand side. So these aren't the limit, they're kind of pieces that work together to give us the limit. Let's talk about our notation here. So this looks a lot like the notation that we saw a minute ago, the limit notation. But do you see the difference here? Instead of saying the limit is f of x, the limit of f of x as x approaches just 2, do you see this negative sign hanging out up here as a superscript? That negative superscript means that we approach from the left. And over here, the limit as x approaches 2, and then I see that plus sign, that positive superscript, it means that I approach from the right-hand side. So be very careful when you're taking limits here to notice if you have a plus or a minus as a superscript behind the number, because that indicates that it's not the limit, it's a one-sided limit coming from a particular direction. So we just said a minute ago that as we approached x equals 2 from its left-hand side, that negative superscript tells me left-hand side, so I'm getting close to 2 from the left. It means I'm traveling on this part of the function. We said a minute ago I was getting close to a y value of 4. And then as I approach 2 from the right-hand side, so I'm approaching from the right-hand side, I'm getting very close to a y value of 2. Oh gosh, that got ugly. Okay, a y value of 2. So because we're approaching two different y values, my graph doesn't actually have a limit as x approaches 2. If the left-hand limit and the right-hand limits are different, then the graph does not have a limit at x equals 2. We say that, or as x approaches 2 rather, we say that that limit does not exist. Okay, let's look at an example here. So suppose that we are given this piecewise function and we're asked to find the left-hand limit and the right-hand limit. So we'll talk about some other ways to do this in 11.2, but right now in 11.1, we're trying to find these limits by using a graph. So let's start by graphing it. So the top piece, f of x or y equals x squared plus 2, that's a parabola, right? That's our basic parent, y equals x squared, that's moved up 1 unit. So instead of a vertex at 0, 0, I'm here at 0, 1, and then I go up 1, right 1, and up 1, left 1, and then from the vertex I go up 4, left 2, and up 4, oops, that was right, and up 4, left 2, right? So there's our basic parabola y equals x squared, which has been translated up 1. I'm using pencil here to draw it because I'm going to erase part of it. I'm only supposed to use this graph for x values that are less than 1. So here's where x equals 1. I only want it where x is less than 1, which means the part's to the left of it. So I'm going to erase this part right here. Now, how about where x actually equals 1? Is that in the domain of this function? No, we only want x values that are less than 1. So let me put an open circle here at x equals 1. That x value is not on this piece. Now, f of x or y equals x plus 3, that's a line. Y-intercept at 3, 1, 2, 3, and then I have a slope of 1. So I'll go up 1, right 1, up 1, right 1, up 1, right 1, and so on. There's that line. Again, I don't want to keep that whole line. I only want to use it for x values that are greater than or equal to 1. So let me erase the part that doesn't have a domain on this function, or on this piece of the function rather. So where x equals 1 right here, that's where I move from one piece to the other. X equals 1 is on this linear piece, so I want to put a solid circle here because that x value of 1 is included. Okay, so now I've got the function. Let's talk about the limits. So we're asked to find, do you recognize what that means? The left-hand limit. So as I approach x equals 1, right here, from its left-hand side, that means I'm on this part of the function. I'm getting very close to a y value of 2. And as I approach x equals 1 from the right-hand side, I'm on this piece of the function. I'm getting very, very close to a y value of 1, 2, 3, 4. So let's do that in pink. So if they ask me for the left-hand limit, it's 2. If they ask me for the right-hand limit, it's 4. If they asked me what is the limit as x approaches 1, not a left or a right-hand limit, but what is actually the limit, here I would say it doesn't exist because the left-hand limit and the right-hand limit are not the same value. They don't agree. Okay, so we just said because the limit as x approaches 1 from the left and the limit as x approaches 1 from the right are not equal to each other, there's no single value that the function approaches as x approaches 1, so we say that the limit does not exist. We say that, and Lindsay Lohan says that in Mean Girls, the limit does not exist. All right, so the limit only exists if the left and right-hand limits are the same. And when we get into the first unit of calculus next year, we actually regularly have to do proofs that a limit exists at a particular point. And our process will be show that the left-hand limit exists, find its value, show that the right-hand limit exists, find its value, and then show that those two values are the same. Okay, so I would like you to take a moment here, pause your video, and try this whiteboard problem. I really want you to use this graph to find the limit as x approaches -2 from the left, the limit as x approaches -2 from the right, the limit as x approaches -2, and then the function value at -2. All right, so hopefully you paused it, did it, and you're back. Let's talk about the answers here. So let's find -2, that's this one right here. All right, so as I approach from the left-hand side, I'm getting very close to a function value of 0. As I approach it from the right-hand side, here's -2, I approach from the right-hand side, that means I'm on this piece, I'm getting very close to a y value at -1. And then, so does, guys, I'm looking at the wrong example. Looking through my notes here, what's going on? Okay, so then does the limit as x approaches -2 exist? No, these have to go to the same number. If they both went to the same value, then that would be the limit, but they go to two different values, so it does not exist. All right, then f of -2, what actually is the function's value of -2? It's -1 down here because that's where I actually see a solid point. All right, give this one a try. Okay, so now as x approaches 0 from the left, I'm on this part of the function right here. I approach a y value of -1. Forgot to close my parentheses. As I approach 0 from the right, I'm on this piece of the function. I'm also approaching a y value of -1. So the left and right hand limits are the same. On both sides, I'm approaching -1, which means the limit as x approaches 0 is -1. How about f of 0, the actual value of the function? Oh, it's also -1. So not only does the limit exist, but this function is also continuous. From the left-hand side, I'm approaching a value that's the same as the value I'm approaching from the right-hand side, that's the same as the actual value of the function, which means if I were to try to draw this, I can draw all the way through x equals 0 without ever picking up my pencil, which makes it continuous. Again, that's an idea that we'll talk a lot more about when we get to 11.3. So here's your very abbreviated assignment. I will let you know that most of them have a couple parts. 29 especially has a lot of parts, but they're real quick because you're just looking at the graph and saying, where's it going to from this side? Where's it going to from that side? What's the limit? What's the function value? So it looks like a lot when you get to that question, but it's not really. It'll only take you a minute. All right, we'll talk later about 11.2. Have a good weekend.